Hi everyone, and welcome along this afternoon. My name's Heather. I'm the event manager for BUILDNZ, and here to welcome Darren Yearsley along to speak to you. Darren is from Waterware, and it's a family business, plumbing, bathroom wear, heating and cooling. He's responsible for system design, commissioning and troubleshooting support. Today he's going to be talking to you about active ceiling radiant heating and cooling using water via the ceiling. So yeah, welcome along, Darren.
Thank you. Okay, welcome. So let's get started. So the first thing we're going to do is just talk about radiant heating and cooling as a general concept, and then we'll get more specific and talk about active ceiling, which is the new technology which we've just released. You can see an active ceiling panel here. I'll talk about the installation options, physically how you run the pipes and connect up the panels, and then we'll just go through a quick case study of a job which we've had access to in California. Okay, so radiant heating is a little bit different from other types of heating where we're manipulating surface temperature to exchange energy. So if we're in a house and we want to heat the space up, we can do that by either warming the floor or warming the ceiling, or if we've got a radiator on the wall, then we can warm the radiator. And we can do the same in cooling mode as well. So if we manipulate the surface temperature of either the ceiling or the floor, then we can change the temperature in the room. When we're doing this with radiant heating, we're manipulating the surface temperature directly, and then the air in the room gets heated or cooled indirectly. So for radiant heating, obviously what we want to do is we want to heat the surface temperature up. And the general principle which we have for radiant heating systems is the larger the surface area that we're manipulating, then the smaller the delta T can be to affect the temperature inside the room. And by delta T, what I mean is if our target temperature in the room is 21 degrees and we're operating in heating mode, then the surface temperature which we have to maintain, for instance in floor heating, is only 3 to 4 degrees warmer than our target temperature. So if our target is 21, then the floor temperature needs to be 24, 25 degrees. And it's the same if we're manipulating the surface temperature in the ceiling, then it's the same. So in heating from the ceiling, then the surface temperature in the ceiling will be the same, 24, 25 degrees. So the advantage of having this close delta T is it's a very gentle type of heat. So you don't get this intense feeling of being actively heated or cooled. You just get this feeling of comfort. So the smaller the surface area, the active surface area becomes, the higher the delta T has to be. So for instance, with a radiator, which is 600 high by 1 meter long, then to heat the room to 20 degrees, you might need a 40 degree difference. So the temperature of the water inside the radiator will be 65 degrees because you're working with a small surface area. And then that will raise the temperature in the room up to 21. The advantage we have when we're heating or cooling the whole surface is the surface area is much, much bigger, which means that the difference in temperature which we can manipulate to becomes much smaller, which gives us much better comfort. So you don't have the perception of if you're standing close to the heat emitter, then you're too hot. If you're far away, then you're too cold. You have a much bigger Goldilocks zone where every area in the room becomes an even temperature. And that's true top to bottom and left to right within the space. So that's really the main advantage of doing radiant heating with these big surfaces is you get a very, very even temperature inside. So intuitively, everyone understands that heat rises, where in fact it's hot air that rises, not heat. When we're talking about radiant heat, that goes line of sight like a laser. So everyone's experienced when you've stood outside on a cold winter's day, and if the sun's shining on you, immediately you feel warm, you feel comfortable. And then as soon as the sun goes behind the cloud, immediately you'll feel cold. That's because the radiant effect from the sun has changed. It's not that the air temperature has changed, it's this radiant effect. So even though the sun's above you, when it shines down on top of you, you get that radiant heat immediately. And the same's true if you're in a outside bar or something like that and they have a radiant heater mounted up high. When that radiant heater goes on, even though it's shining down from above, immediately you'll feel the warmth on your head. And that's quite an important distinction with these different types of radiant heating. And it's another illustration of the smaller the surface area of the heat emitter, then the hotter that heat emitter has to be to heat the room. So the classic example is when you're outside in one of these bars and you have a high level heater, but the surface area is only small. That has to be very, very hot to be able to heat you in an outside environment. And the disadvantage with that is if you're standing close to that emitter, then you get a very strong heating effect. If you're far away, then it's much more gentle. So this Goldilocks zone of comfort is reasonably small. The advantage which we have when we're heating a complete surface, such as the floor or the ceiling, is you don't get that effect. So the entire room becomes heated evenly. And we can take this general principle and we can also expand it into cooling. So if we actively cool a surface in the room, then the opposite happens. That surface turns into a heat absorber. So if we're in cooling mode, for instance, and our target temperature is 21 degrees, if we lower the slab temperature to 20 or to 18, then the walls, the ceiling, the people, the table, the chairs, everything that's inside that room immediately will start to radiate energy into that colder surface, because nature's always trying to find a balance. And the same's true with the ceiling. But the advantage we have with the ceiling is that because you're not walking on it, then we can make that ceiling temperature much lower without affecting the comfort. So you might find in cooling mode, if your target temperature is 21 degrees, then your ceiling will be operating at 16 to 17 degrees surface temperature. And so it becomes a very powerful heat absorber. So the walls, the floor, the body, the table, the chairs, they all start radiating energy into the ceiling, which then gets taken out from the room. And so that's how we can manipulate the comfort inside the room, both in terms of heating and cooling, is by manipulating the surface temperatures in those rooms. The advantage which we have with the radiant cooling system is because we're just working with changing the temperature of the surface, we don't have any noise. So when the system is active, you don't get any sort of noise of the system running. There's no fan noise. You can't hear the water circulating reasonably slowly. So you just get the effect of the comfort of the heat being absorbed from your body, but you don't get any of the stress of a normal air-based system where you've got wind blowing on you, where you've got the noise from the air conditioner unit. And also the other advantage is that you're cooling down the bones of the house. So the ceiling, the walls, the floor, the table, everything has energy taken out of it, but not directly the air. So the air gets indirectly heated or cooled from the surfaces, but we're not actually heating or cooling the air directly. So the advantage of that is you can have your doors and windows open. Let's say it's high-end residential and you've got some stacker doors which you leave open. You can come inside and have the cooling effect, even though you've got free flow air going through the house. So it's a very, very nice cooling effect which you can have. With a traditional air-based system, you have to keep it closed. So if you open your doors and windows, the cold air just flies away. But that's not what happens with a radiant cooling system. So why radiant? Radiant maximizes the comfort in the space. So for the reasons that we've talked about. Number one, because we're working with such a big surface area, the temperature difference which we're working with is very compressed. So in heating mode, if our target temperature is 21 degrees, then our surface temperature will be 25, 26. And in cooling mode, if our target temperature is 21, then the surface temperature will be 15, 16, something like that. So because the difference in temperature from the target temperature which we're trying to achieve and the radiant surface which we're bringing the temperature down or up, then you get a much more even, gentle heat in the space. And that makes it very, very comfortable. So the second reason why we use radiant is because it minimises the environmental stress. So the environmental stress comes in a number of ways. If you're doing an air-based system, then you have the stress of the air from the fan blowing on your neck, for instance. Nobody likes that, it's not very comfortable. You've got the noise associated with the fan running. You've got the possibility to transmit disease from one station to another. So if you're in an office environment or if you're in a healthcare environment, you don't want to be transporting air from one area to another. With a radiant-based system, there is no air movement, so you're not spreading these things around. And we also have reduced life cycle cost. So again, because the temperature which we're trying to maintain is so close to our target temperature, in heating, the water temperature we'll be sending is probably about 30 degrees. So there's about a 4 to 5 degree difference between the water temperature we send and the surface temperature that results. So in a ceiling-based system, we'll be sending 31, 32 degree water, and then the surface temperature on the panel will be maybe 26, and then the resulting temperature in the room will be about 21. And then in cooling mode, it's the same. So the cooling mode will be operating maybe from 10 degrees to 18 degrees, depending on the dew point, to result in a surface temperature of between 15 and 18 degrees. So the advantage of that is with the new high efficiency appliances, what you find is the lower the water temperature, the higher the efficiency. So if you can maintain in heating a cooler water temperature, or in cooling a higher water temperature, but still maintain comfort inside the space, your running costs will be the minimum they can be. As an example, we have the system in the Waterware offices, which we commissioned this year in January. And through the summer, the real-time COP which we got out of our system in cooling was 5 to 1, and in heating, we're running at about 4 to 1. So COP means coefficient of performance, which is basically the efficiency of the appliance. So for 1 kilowatt worth of electricity we send to the heat pump, we can absorb 5 kilowatts worth of heat. Or in heating mode, we send 1 kilowatt to the heat pump, it'll generate 4 kilowatts worth of heat. So if you're talking about that in terms of efficiency, like a boiler efficiency, then it's 500% in cooling or 400% in heating. So it's quite a marked improvement of efficiency. One of the other advantages we have is because you're working with a completely flat surface, with either a floor or a ceiling, there's no ducts or no vents to clean. So in where you're actually delivering the heat or the cool, you don't have any maintenance as far as the ductwork or the vents are concerned. So you don't have to control for dust, you don't have to control for bacterial infections living inside the ducts. It's also completely invisible. So from an architectural point of view, you're working with completely clean flat surfaces. So you don't have vents or anything like that which is visible to the eye. And also, obviously, it's silent in operation. When it comes to moving energy, it's much more efficient to move energy using water than it is using air. So, for example, a zone of radiant either floor heating or ceiling heating, we can run up to 30 square meters from a pair of 16 mil pipes. Where to do that with an air-based system, you need a duct 100 by 200. So when you're in an architectural environment and you're trying to compress the size, or where you've got a difficult path with a flat roof and not much space, then it's much easier to route 2 small pipes than it is 2 large ducts. So that's a good advantage for some applications. The last advantage we have is very flexible zone control. So every area we can operate independently in terms of temperature. So because of the structure of the system, the way it's installed, it's very easy to give different performance in different areas. So you can thermostatically start and stop each one of the zones independently. Okay, so more specifically about active sealing. This is an example of a panel here. So this is designed to go behind the jib, and then you put a normal jib over the top. You have your 2 pipe connections here for your water in and your water out, and then your heat emitter is basically in these smaller pipes here. So Radiant heating and cooling has been around for a long time, especially radiant heating, but also radiant cooling to a degree. It used to be that in these older buildings, mostly made out of masonry, they'd have very, very thick walls, 3 to 4 feet thick, and what they would give you is a very stable indoor temperature, where in the summer it would stay nice and cool, and then in the winter it would be nice and warm. And the way which this technology worked was the energy from the person, from the body, would be absorbed into these walls, and because there's so much thermal mass, it keeps a very even indoor temperature. So the active sealing concept has the same sort of effect, but rather than having to have high mass of lots of concrete, we can do it by moving water backwards and forwards to transport the energy either in or out of the zone. So Masana, who manufactures these panels for us, they're based in Italy. Their first sealing installation was done in 1997, so 30 years ago. There's over 10,000 systems installed worldwide, mostly in Europe, but also they now have a satellite office in California, and they're doing a lot of installations, high-end residential in California. Their general split, as a rule of thumb, is 60% commercial applications, so it'll be rest homes, hospitals, airports, hotels, those types of things, schools, and then 40% high-end residential, where we've got very demanding clients. They want to have a heating and cooling solution, but with zero noise, zero air movement. So maximising the comfort. Okay, so heating performance. So when we're comparing to underfloor heating, to give you a comparison, if we have an underfloor heating system and we standardise on 200 centres in the floor, and the normal water temperature, maximum water temperature you send be 45 degrees, so with 45 degree flow, 35 degree return, we can achieve about 100 watts per square metre. So to put that into context, if you're in a room which is 4 metres by 5 metres, that's 20 square metres, you can add 2,000 watts or 2 kilowatts into that room using floor heating with that sort of structure, 200 centres, 45 degree flow. With the Masana panel, the output is about 40% higher. So with a 45 degree flow, we're at about 140 watts per square metre. So that gives us the flexibility of not having to cover the entire ceiling to reach the heating, the required heating load. So typically, if we're doing a heating only system, you only need to cover 40 to 50% to reach that 100 watts per square metre threshold, which most systems operate with. So the operating water temperature in heating mode typically is 25 degrees to 45 degrees, which gives us a surface temperature on the panel from 21 to 40 degrees. Generally speaking, you won't have to achieve that higher surface temperature to maintain comfort inside the room. It would only be if you're right at the low end, maybe 35 to 40% coverage, then you have to increase the water temperature to compensate. But for most systems where you're running at 50% coverage, or if you're doing cooling where we use higher coverage, then you can reduce the water temperature right down to 28 to 32 degrees typically. So this system's very well matched to the new high efficiency appliances. So air to water heat pump, gas condensing boiler, it's a very good fit to those two appliances because they natively produce water in those sort of temperature range. So air to water heat pump operates 25 to 45 degrees, and then a gas condensing boiler is the same, but you can go higher. It's a very good fit for a temperature compensation system. So the way temperature compensation works is if your building doesn't require a lot of heating load, then you can lower the water temperature to reduce the output from the panel. So you can see from this graph here, if we're sending water at 30 degrees, then we have 61 watts per square metre, and if we're sending at 45, we have 140 watts per square metre. So you can increase or decrease the heat that you put into the building by making the water temperature either higher or lower. So what a temperature compensation system does is it measures the outdoor air temperature, makes an estimation for how much energy is required in the building, and then it electronically changes the water temperature up and down to compensate. So the advantage of the system is you increase the COP of your appliance, so your efficiency goes up, but also you increase the comfort in the system. So the control system becomes a preemptive control rather than a reactive control. We don't wait for the house to either overheat or underheat. In advance, as soon as it gets warm outside, we decrease the water temperature. Or in advance, as soon as it gets cold outside, we increase the water temperature. So it electronically goes up and down to maintain a very even temperature inside the house, because we're always trying to maintain comfort. Okay, so for cooling performance, we have very much the same. The output from the panel, we're bounded by the dew point. So the dew point is when condensation forms. And so when you're doing radiant cooling by manipulating the surface temperature, it's very, very important to respect the dew point. So if you drop below the dew point, condensation will start to form. If you stay above the dew point, then condensation will be eliminated. So the way these systems work is they calculate what the dew point is and then electronically change the temperature inside the appliance. So it works very much like temperature compensation, but in cooling mode. So normal operating temperature for the ceiling panel when you're working in cooling mode is between 16 degrees down to 10 degrees. Generally speaking, you can't get much below 10 degrees without bumping into the dew point. It depends on your humidity. There's some areas in New Zealand which have very low humidity, like Wanaka, for instance, which is normally about 30%. There you can go as low as 8, but generally speaking, we'll design the system to be able to maintain comfort at 10 to 12 degrees minimum, scaling up to 18 degrees as your humidity rises. So the level of performance which we're achieving, if you've got a 70% coverage, then you're achieving about 50 watts per square metre of heat absorption. So in real world application, that allows us to lower the indoor air temperature by 7 to 8 degrees. So to compare that to a floor-based system, if you're doing slab cooling and you're walking around on the slab, then the limit that you can get to is about 3 to 4 degrees reduction before making the slab too cold and then impacting on the comfort, and also being in danger of then tripping over the dew point. So one of the issues with slab heating is it has a lot of what we call thermal mass. So it takes a very long time to heat up, but also takes a very long time to cool down. Now, if you have a rapid change in humidity, it means that you can trip over the dew point, because what your dew point was half an hour ago is now lower than what it is now. It means if your surface temperature on your concrete is below the dew point, then you'll start to create condensation straight away. The advantage with your ceiling-based system is it's very low thermal mass. So you can change the surface temperature within 10 to 15 minutes. So it means that you can be much more aggressive with your dew point management and run that temperature up and down on demand. So we can get about twice the amount of power. So with a floor heating system, we're 3 to 4 degree indoor reduction. So that's like going from 25 down to 21. With a ceiling-based system, we go to 7 to 8. So it's like 29 down to 21. So for most New Zealand applications, that's more than enough power to maintain comfort. So again, the surface temperature on the panel is 3 to 4 degrees higher in cooling mode than what the water temperature will be. So if we're sending 10 degree water, the resulting surface temperature will be about 14 degrees. And if we're sending 16 degree, the resulting surface temperature will be about 20. So you do get a little bit of room up your sleeve to avoid the dew point. If you're sending water at close to dew point, you've always got a little bit of tolerance built into the panel. So these systems are always powered by a heat pump. If you're doing a cooling system, then you have to have a heat pump. Obviously, you can't cool with a gas boiler. If you're doing heating only, then yes, you can connect it to a gas or diesel boiler, no problem. But if you're doing both cooling and heating, it has to be an air-to-water heat pump, and it has to have dew point management built in to avoid condensation. Okay, so the whole point of these systems is to create optimal comfort. And how that's achieved with a radiant system is again by compressing that dew point, the temperature difference around the operating system. So if our target temperature is 21 and we're in cooling mode, then we're about to achieve that with a ceiling temperature of maybe 18 degrees, 17, 18 degrees. Because of our very large surface area, we only need a small difference in temperature to be able to pull out that much energy from the room. So when you're looking at the system when it's operating in cooling mode, at the top of the room will be 18 degrees, at the middle of the room will be 21, and then at the floor will be 22. So there's a very small difference in temperature from top to bottom, and then none from left to right. So it means that when you're standing, you have the same experience as when you're sitting. And the same's true in heating. So in heating, obviously, we're going above target set point. So if we're trying to get to 21 degrees, then surface temperature on the panel will be 24, 25. And then your floor temperature will be 21. So you get a very, very small difference in temperature gradient, both up and down, left and right. So it creates this very high level of comfort. So it's not like an air-based system or, to a degree, a radiator-based system where you've got a smaller surface area, and so you have to operate with a bigger difference in temperature to affect the whole room. So with an air-based system, if you're sitting right underneath a duct and the duct's blowing on you, you'll be too cold if we're in cooling mode. You have a Goldilocks zone of about 1 meter where you're comfortable. And then if you're further away than that, then you're too warm. So the comfort that you can get in the system is always limited depending on where you are relative to the vent. With a ceiling-based system, because almost the entire ceiling is heated or cooled, you don't have that same level of difference in temperature depending where you are relative to the heating or cooling element. Okay, so the other advantage which we have with the ceiling-based system is it minimises environmental stress. And what do we mean by that? Okay, so environmental stress is wind blowing on your neck, for instance, from a fan. It's not very comfortable. Everyone's experienced that where you've got wind blowing on you. We've got noise. So if you've got a fan-based system, there's always some noise component to it where you can hear the system droning away. With a radiant-based system, it's totally silent. So when you're inside, you can't hear anything. You don't actually know the system's going other than being comfortable. We were talking about even distribution of heat. Because we're using the entire ceiling as our heating element, you can't really get away from where the heat or the cool's coming from. So it doesn't matter where you're sitting in the room, everyone has the same experience. And we're not pumping viruses and germs and stuff around the room or from room to room. So because these systems, we're not doing any air movement, it's all radiant, then we're not transporting bugs around. That's very, very important for healthcare, for hospitals, also for the office environment. We've got one person sick in your office and then the whole office gets sick. A lot of the time that's because the air conditioning system's blowing that around and everyone gets a little taste. Okay, so why does a radiant system cost less to run? There's a few different reasons. The first primarily is physics, where water is a lot more dense in terms of energy than what air is. And it's much cheaper to pump water than it is to blow air with a fan. So the amount of watts required by a fan to move the right quantity of water for your heating and cooling duty is much higher than the watts required by a pump to move the water around. The second is because we're using such a big surface temperature, surface area, and we've got a small difference in temperature between our target temperature in the room and the surface temperature we're trying to operate on the panel, means that the water temperature that we use is the lowest possible in heating and the highest possible in cooling mode, which means the COP from your appliance goes up. The other saving is you get a higher level of comfort with a radiator system than you do with an air-based system at a lower indoor air temperature. So if you're in a air convection-based system, to be comfortable in winter, typically your room temperature has to be 23, maybe 24 degrees depending on the person and depending on the solar, the radiant coming through the windows. Where when you're in a radiant-based system, you can maintain comfort at a much lower indoor air temperature. 20 to 21 is normally satisfactory for most people. So because you're maintaining the temperature in the room at a lower level, it means that the energy escaping from the building is less, so the running cost is less, because you have to replace less of that energy. And then the last saving is on surfacing costs. Because you're basically working with a completely flat surface, then there's no cleaning as far as vents and ducts are concerned. All you have is a standard ceiling. So the maintenance cost is much less. Okay, when we're looking specifically at the installation, so we've got two types of panel. We've got a residential panel and we've got a commercial panel. So this is the residential panel. This is a half panel, so the standard panel length is 600 wide by 2.4 meters long. You can split them in the middle to space them apart for running services, so for mounting your lights and smoke alarms and things like that. The panel construction itself is just polystyrene, aluminium and pipe. Very lightweight construction, so the panel itself is only a couple of kilos. It's very easy to install. And you can retrofit as well. If you're in a high stud environment, so 2.7 and higher, and you want to retrofit the system, then if you can drop your ceiling height by 50 mil, you can apply this over the existing ceiling and then re-jib. Or obviously for a new install, it goes inside the ceiling battens. So here's an example of how it's physically managed on site. So the way the system's set up is depending on what coverage you need. Let's say, for instance, a heating application, and you need 40% coverage to meet your heating load. Then you set your ceiling up using either rondo or standard wooden battens. The battens need to be 38 mil to 40 mil, and these panels sits in between the battens, and then basically you jib over the top. But what that allows is to have some clear zones to run your services and then some active zones to do your heating. So for instance, you might have 600 mil with your heating panel, 400 mil with clear zones for your lights, your smoke alarms, your sprinkler if you have that, 600 active, 400 clear, 600 active. And then you've got the ability to also split the panels. So if you've got a panel which is 2.4 meters long, you can cut it in the middle, split it apart by 200 mils to then mount lights in the center of your active zone if you like. So when you come to do the installation, the panels basically get installed from the heat installer. He does his pipework connection, then your Sparky will come along, run the wires, and then your jib stopper comes along, plasters the ceiling as per normal. You can use any jib, any standard fibre board in the New Zealand market, so it doesn't matter whether it's 13 mil or 17 mil, aqua line, noise line, fire line, doesn't matter. So you jib the ceiling as per normal, and then that gives you a completely finished surface. And it gives you a complete division of trade. So it means that your heating engineer is not getting in the way of any of your other subtrades. So the system's left under test while the construction's completed. If there's a problem and you hole a pipe, then it's repairable. You have to repair the ceiling, but it's easier than repairing a floor if you've got a floor heating system, for instance. And to give you an idea of the coverage, we can cover up to 30 square meters of heating with one pair of 16 mil pipes. So it's much easier to route two 16 mil pipes than it is some ducts, for instance. And it gives you complete zone control then. So you can have a zone for each bedroom, one for your kitchen, family dine, whatever you like. So it means you can maintain different temperatures in different areas. So the commercial panel. Okay, so the commercial panel is designed to go into a suspended ceiling. So it's a standard panel which is 600 wide by 1200 long. You can basically pop out your existing panel and drop this in, make the pipe connections, and then you're good to go. So it's very easy to retrofit for the commercial system, or obviously a new system isn't a problem at all. So there's a wide design of tiles. So this is the acoustic one, but there's all sorts of tiles which you can get and different visual looks. There's no special skill required. It's very basic to install the tiles. Basically, you push the old one out, drop the new one in, and so then you can both retrofit and new build. So this is from the Waterware office. You can see there's two types of panel there, or three including the LED light. So in the corner we have the LED light. We have the active panel with the holes in it, and then we have the standard panel which is next to that. So you can see the contrast in the room. In the Waterware office we're running both floor heating and ceiling heating, and the ceiling heating is only about 30% coverage because we've got both systems working in tandem. So it allows us to lower the coverage on the ceiling. But it's a very good system. We can run up to 24 panels from one set of 16 mil pipes, which allows you to do zone control. So in the Waterware offices, we've got one zone in the boardroom, one zone in the office, and then one zone in the showroom. Okay, so here's an example of high-end residential. This job is in California, constructed in 2013. So Masana has an office in California, and this particular house, very high stud, large footprint, almost 400 square meters, and the cooling duty there is very high. So the outdoor temperature they have is 39 degrees, so it's very hot, and the target temperature inside they want 20 degrees. So it's by far the most stressful application that I've seen. They're doing the cooling in this place using radiant only, so there's no air-based system at all, and they have the ability to maintain a 20-degree indoor air temperature even when it's 39 degrees outside. Okay, so a previous generation panel had the jib attached to the panel itself. The new one, we're going with the naked panel, which allows the division of trade. But it gives you an idea here of the ceiling coverage required in this job was 70%. And you can see that the services, where the services are run in between the panels, so you've got your lights, your sprinkler and your smoke alarm, basically in this channel in between the panels. And here's the system operating. So on the left, obviously that's a picture of the ceiling. They had some wooden surrounds around the panels. And you can see the surface temperature there, which they're achieving, is 14 degrees. So operating in this system, we're seeing 10-degree water. It's very dry in this place in California. It's up in the mountains. So avoiding the dew point is reasonably easy. So they can send water temperature to the system at 10 degrees, which is giving them a 14-degree ceiling temperature. And then on the floor, the surface temperature they're maintaining on the floor is 18 degrees. And so with this setup, they can have the indoor air temperature at 20 degrees when it's 37 degrees outside. So it's a very, very strong cooling effect with this dual-based system. Okay, so who is Waterware? Let's give a little brief about us. We've actually been in business for 30 years. We started in 1989. We're a family-based company. There's 30 of us. Me, my brother and my sister operate, and then we have some other family members in logistics. Where about 40% of our business is central heating and now cooling, and then the rest is bathroom wear and commercial plumbing products, pressure control, temperature control, those types of things. We're mostly a niche supplier. As you can see from this system, it's very specialist, and that's really our bread and butter, is these sort of high technology, very niche products which need a design component to them. And that's what really spins our wheels. That's what gets us excited, is doing these types of special products. Based in East Tamaki in Auckland. So here's some of our brands. In the heating side, we use the Valent German manufacturer for our gas boilers and for our air-to-water heat pumps. That has the dew point management built in. And then Masana is the panel supplier. And then Heatmiser is our controls package. Okay, that's it. So thank you very much for your time, and let me know if you've got any questions.
I was wondering whether, if you have an existing in-slab system with an air-to-water heat pump, whether you can use the same heat pump to extend and do part of your building in slab heating and part of your building in the radiant ceiling panels.
It depends on the size.
Style, I suppose.
Yeah, it depends on whether you've got excess capacity in your appliance or not. So generally speaking, the appliances come in a range of sizes. Like for instance, single phase appliance, we do a 10 kilowatt and a 16 kilowatt. So if you're in between sizes, if you needed a 12 kilowatt for your heating duty and you've got a 16 kilowatt appliance, then that gives you 4 kilowatts worth of extra capacity, which you could use, yes. To give you an idea of a retail price, I priced a system the other day where they wanted the two options, where they wanted to have a floor heating system or possibly active ceiling, depending on the pricing. and I think the house was 250 square meters, something like that, at a retail, including installation, so a full retail price with all the components, with the underfloor heating system doing heating, cooling, and hot water production, but with the slab. The retail price was about 40,000, and then the equivalent active ceiling system was about 50,000. So it is a significant investment, but it raises that level of performance from a 4-degree reduction in summer to an 8-degree reduction. And it also allows you complete flexibility with your floor coverings then. So if you want engineered wood or a high performance carpet, something like that, that all reduces the performance in your floor heating system, where typically there's nothing between you and the ceiling, so you've got complete flexibility then. All right, thank you.